Okay, great. Thank you. Okay, welcome everybody. Thank you for coming to our first seminar of the semester. It's a pleasure to have here Dr. Alex Ihler from UC Irvine. Dr. Ihler is a professor of computer science at the University of California at Irvine. His research interests are in machine learning and algorithms, and with all sorts of applications, including sensor networks, computer vision, and data mining. Just for full disclosure, Dr. Ihler actually comes from the same group I worked in a long time ago from MIT. He's a student of Alan Wilsky, and it's a pleasure to have you. Thank you for coming.
Thank you. Thank you for having me.
Yours. No?
All right. So today I'm going to talk about approximate inference in graphical models. And graphical models have become a very powerful tool for expressing uncertainty and probability distributions over large, complex systems. So you can imagine that we have a system of many variables, say x1 through xn. We'll take these as discrete random variables. And so if n is pretty large, then actually representing this probability distribution is extremely difficult. So if I actually tried to create this table of all possible outcomes of x1 through n, it would be exponential in the size of the system. And so it would be very difficult for me to actually represent or manipulate. So graphical models help us by describing structure within that system as being constructed from a collection of smaller functions or factors, which I'll just write as psi, over smaller subsets of the variables so that we can actually represent them and manipulate them. So you can think of this distribution as being a product of a bunch of smaller factors psi, each over some smaller set of variables alpha. Often this distribution isn't normalized, so there's a normalization constant z, also called the partition function, which is just the sum over all the possible configurations. So this might be very difficult to compute, as we'll talk about later. This is a very general formulation, and graphical models come in a lot of different flavors. So you might be familiar with one or a different one. In artificial intelligence, often Bayesian networks are used. So these are directed graphs that use factors that represent conditional probabilities. Markov random fields have a long history in statistics, statistical physics, and many other areas. And more recently, factor graphs have emerged as a nice unifying representation. They got very popular with error-correcting codes, and now they're one of the de facto formulations. So often, because I'm a little too lazy to draw a lot of low boxes, I'll draw Markov random fields. So we'll just, you can imagine that you have a graph in which each of the nodes of the graph is associated with one of these many random variables. And the functions themselves are associated with the cliques, the fully connected sets of those variables on the graph. So for instance, here we might have functions that are over, say, pairs of variables. And then we would draw a graph that looks like this, where every pair of variables that's involved in some function is connected by an edge. So what do we actually want to do with this? This representation is only useful as far as it lets us solve interesting and hard problems. And generically, anything that you want to get out of the system once you've built the model is called inference. So we imagine that someone's given us this model, and where that comes from is an entirely different problem. What we want to do is extract some kind of information from it. So we've got the model. We'd like to answer some query. Often we'll see that this is combinatorially hard, so we'd like to have some approximation algorithms that will make it more efficient. And since we're going to be required to approximate things, sometimes it'll be very useful to get bounds or some other kind of optimality certificates from our solutions. I've been lucky to work on problems in many, many different areas, often with different collaborators. So just to suggest some of the places where graphical models are very useful. As Hamid mentioned, I did some work while I was a student of Alan Wilsky's and John Fisher's at MIT, using these for sensor networks. So you can treat the localization problem in sensor networks, where you're trying to estimate the positions of different sensors given measurements. as being a graphical model where the measurements define the relationships between small sets of sensor positions. And if you run an approximate inference algorithm on that, you'll get estimates of where the sensors are. I also do work in computer vision. So most of these pictures are with Charles Fowkes and our student Julian Yarkoni, working on problems like image segmentation or on stereo vision, where each of the variables is associated with a pixel in the image, and your goal is to estimate the depth of field given two pairs of images, like from your eyes. And there, the model is encoding some kind of smoothness prior. So this is an image processing kind of problem. Also, I've worked in computational biology. So work I've done with Ram Metu, who's now at Tulane, on predicting protein configurations or binding energies. You can represent very complex problems using these kinds of local structures. So you imagine that the energy of some protein configuration is related mainly to energy of interactions of nearby parts of that model. Also, linkage analysis, studying how genetic factors influence disease, and using pedigree charts to try to understand what the system, who might have the genetic markers within their family. So all of these are different types of inference problems. The most common two inference problems are probably either MAP estimates, computing the optimal configuration of some problem. So we have a graphical model, and we'd like to compute the optimum, the most likely configuration of the whole system. So this is a combinatorial optimization problem. And summation type tasks where we'd like to sum out the variables in the system. So classically, this is represented as a partition function. If I give you an unnormalized model, you want to compute the normalization constant. Other common uses for it include computing the marginal probabilities from which you can make Bayes optimal estimates of a particular variable. It also has to do calculating the partition function can be used to calculate the probability of some observed data and do likelihood ratio tests and other kinds of decisions. One kind of problem that is not very well studied at the moment, and that I'm going to try to talk about today, is mixed kind of inference queries. So mixed inference queries are really just any inference problem that involves more than one of these types of elimination operators. So here we're eliminating all the variables with summation. Here we're eliminating all the variables with a maximization. In mixed problems, we have perhaps some of each, perhaps even other operators like min. And a classically hard example of that is a task called marginal MAP, where we'd like to find the optimal predictor of some set B. So not just a particular variable, but some set within the model. But we need to marginalize out the rest of the model. So this is not very well studied. People usually replace marginal MAP queries with regular MAP queries, where they compute the optimal estimate of the entire system. But I'd argue this is not a good idea. And here's just a little toy example to illustrate it. So here's, say this is my trivial probability table over whether it's rainy or sunny at home in Irvine, and whether I walk or drive to the office. And so you can see, right, most of the time it's sunny, but if it's rainy, I tend to drive. Right, so my decision is based on the weather in some sense. And I can say, from this joint model of the whole system, what will the weather be like tomorrow? Right? So if I solve the entire system using MAP, it'll find the joint most likely configuration of that system. And so the prediction there will be that it's rainy and I will drive. And the common usage of that would then to just be throw away the variables I'm not interested in. So I'd predict that it's rainy. But this is absurd, right? The correct prediction should be that it's sunny. And in fact, it's more than absurd, because the prediction that I make using a standard MAP, finding the most likely joint configuration, depends on my policy, right? If I buy an umbrella and I stop driving as much, then suddenly it'll switch. So that's not a kind of property that we want out of our inference algorithm at all, particularly if we're going to reason about decision problems. Another kind of mixed inference problem are multi-agent decision problems, where you've got random variables and other policies that are being optimized over. Okay, so the reason people don't think about these kind of mixed problems is that there's a hierarchy of hardness in these systems. So maximization is the easiest, being only NP complete. Summation is sharp P complete, and this is something like P to the NP. So everything is getting harder and harder as these problems progress downward. So if the very simplest of these is NP complete, well, we shouldn't give up, I hope. But we want to focus on approximation algorithms. Right? We can't hope that in every problem we'll be able to solve it exactly. So we should try to figure out what we can do to do well on most problems. Okay, so I'll give a background on approximation methods, looking at it from two views before I present our generalization of those methods next. But I'll start off with a classic view, which is to just use variable elimination. So to just walk through the operations of the inference procedure. More popular now have been variational algorithms, like message passing algorithms, such as belief propagation. These have really proven to be incredibly powerful and have really changed the field in many areas. And in fact, these turn out to be closely related, so I'll discuss that as well. So elimination algorithms are essentially just a smart way of doing the procedure itself. So suppose I have a graphical model. It's a product of a bunch of smaller factors over pairs of variables. So here's the graph that it's associated with. There are 5 variables and 6 factors. And if I want to perform this sum, I want to sum out over all the different configurations of variables. So suppose I decide to sum out over x1 first. Most of these factors don't involve x1. So I can just distribute the sum inward until I collect only those functions that do depend on x1, and then sum them out. Right, so this is an algorithm. It's being framed as an algorithm called bucket elimination. There are a lot of equivalent ways of doing it, but it's sort of useful. You can think of the factors that are incident to the variable as going in a bucket. I collect those together and then eliminate the variable. And that produces some new function. Right? So I take the product of those, sum out x1, and I get a new table over the remaining variables. Put that into the new system, and then find some other variable to eliminate over. And so collect all the variables that depend on x2, sum them out. I'll get a new function, collect x3, and so forth. So this is just a smart way of organizing the original computation. But it turns out that because the cost of this is related to the size of these tables that you're representing. So if I have any table that's over d variables, then, k variables, then I have d to the k entries in that table. So the cost of doing this procedure is going to be exponential in whatever the largest table I encounter is. And the smallest such thing over any ordering is called the tree width. So it's exponential in a parameter of the graph, a property of the graph called the tree width. One nice thing about this view is that this same procedure can be used for any elimination operators. Yes?
What's a typical tree width?
It depends on the problem. Often much higher than you can deal with. So in, I guess, the competition that's running right now, I don't know what the actual competition values are, but our practice problems have tree width 30 or 40 at least. And pretty much, even if things are binary, anything over 20, you're in trouble. You can probably manage a little less than 20. Other questions? Okay, so this procedure works no matter what these elimination operators are. So I showed it for sum, but if you replace it with max or any collection of elimination operators, the same thing just falls through. But the reason that having some mixed set of inference problems is much harder than all sums or all maxes is that you have that the operators don't commute. Right? So if I have a max outside and a sum inside, I can't swap them so as to reduce my tree width by choosing a different ordering. So for instance, here's a graph which is trivial to solve if you maximize over everything or sum over everything. So it's just a hidden Markov model. But if I tell you that I want to sum out all of the hidden chain nodes and find a maximizing configuration of these hanging on leaves, the problem becomes really hard. Right? So if I sum this out, I'm going to slowly build up dependencies between these max nodes. By the time I finish summing out the hidden chain part, I'm going to have a complete clique over all the rest of the graph. So my cost is going to end up being exponential in the size of the graph, even though it's a tree-structured graph. So I think this is basically the reason that these problems haven't gotten so much attention, is even with fairly easy-looking problems, you can end up with computationally intractable tasks pretty quickly. So even with sum or max, these operators grow too large too quickly. So there have been a bunch of approximation algorithms. And the closest thing to variable elimination is something called mini-bucket. So mini-bucket says, what I'm supposed to do is collect these three functions together and sum out x1, and I'll produce a table over the remaining three. So if I imagine, OK, let's say that's too hard. I don't want to deal with such a large function. So what I'll do is I'll take the three variables and I'll form them together in smaller groups, whatever group size I can manage. So here I might pair these two together, and I might leave the last one separate. And then I can eliminate separately in those groups. So you can actually bound the function that's produced by this sum by the product of two functions, one of which is the sum over one group of tables and the max over the other group of tables. So these are the bounds that the classic mini-bucket uses. And then just treat these as two new functions, put them in the procedure, and continue. So it's just a minor modification. Right? It works by using this inequality. One thing you can think about here is you can imagine that instead of having one variable that you were eliminating to produce the graph over the rest, you can imagine you've made two copies of that variable. So you've split it into two parts, one of which is connected to those two factors, the other which is only connected to one factor. And then you've also modified whatever this elimination operator is. So we'll go into that in more detail in a minute. But it's useful to have this view of things as this approximation as copying or splitting variables in some way. So this is what I'll call the primal view, sort of direct combinatorial elimination on the graph. More recently, people have used variational algorithms like belief propagation to do very well on these kinds of problems. So let me explain variational methods a bit as well. This is a very different seeming perspective, although they're quite connected. Variational algorithms take this problem, either the combinatorial optimization or the combinatorial sum, and replace it with a continuous optimization over distributions. So you can think, so let's say I'm trying to optimize my distribution P of x. I could change that problem into, instead of finding the configuration x star that maximizes it, I could ask for the distribution over x that maximizes the expected value. Right? So if P of x has a single maximum, then the distribution that will maximize this thing will just be a delta function on that point. And so really this hasn't changed anything about it, except instead of being a discrete optimization, now I can frame it as an optimization over distributions. There's a similar form for calculating the partition function. So in that case, it's an expected value plus an entropy of the distribution. So I optimize over distributions of this form. And this might look a little mysterious if you're not used to variational methods, but it's actually quite trivial. So you can just prove it by writing the Kale divergence between P and Q and doing a little bit of manipulation. And you end up with this inequality that the partition function is less than the expression that I wrote here. And they're equal if the two distributions are equal. So this thing will be maximized by choosing Q equal to P. Okay? So this is just a reformulation of the same problem into a continuous optimization. In some sense, it doesn't help, because I told you before that P was too large for us to deal with, too large to represent. So how are we going to represent Q and optimize over it? The really useful thing here is that it's a rewriting of the problem that lets us devise new approximations, different approximations from the combinatorial view before. So what you can do is, first you can note that this expectation actually, because this inner part is a product of terms, it splits into a sum of expectations. And each of those expectations is only over some small set of variables. So you can think of those as the marginals over the cliques. And then we can approximate each part of this in different ways. So for instance, we can approximate the set on which we're optimizing the distributions by either thinking about only a small set of distributions that are easy for us to represent, or by relaxing it, optimizing over parameters that don't even correspond to a distribution. And in fact, since you have this representation in terms of a sum of a bunch of smaller things, you can think of optimizing each of those things individually and trying to force them to be consistent with some global distribution, but perhaps not actually enforcing that entirely. So different sets of approximations here, different relaxations of the constraint set, and in the summation case, different choices of the approximation to the entropy lead to a slew of different algorithms for solving these problems. So the most common is something called loopy belief propagation. It really revolutionized error correcting codes about 10 years ago, a little more now. And that replaces this set with a relaxed set. So you look for beliefs that are not necessarily consistent with distributions, and you replace this entropy with an approximation called the beta free energy from physics, and you get an approximation to this form. So Hamid said in an earlier meeting that everything we're doing, some physicist has done before. So this is definitely, right, a lot of this was in some sense reinvented by engineers, and then statistical physicists realized what we were doing and have told us about some of the background. Other variations give you different properties. So for instance, you can get upper or lower bounds using something called tree reweighted belief propagation, or our version, which is negative tree reweighted. And that just corresponds to a different substitution of the entropy approximation. Another one gives you other upper bounds, something called conditional entropy decomposition. And mean field will give you lower bounds on the partition function. So that's a different replacement of this constraint set. So this has led to a lot of different algorithms that can be used to approximately solve either of these problems. So you can think of this as a grid of different algorithms that we could use and perhaps what their properties are. So sum and max are sort of the most commonly considered problems. So sometimes I write things in terms of psi, and sometimes in terms of theta. It's just a logarithmic transform. So people who work on belief propagation tend to use exponential family forms, and that's using this theta. So if you see theta, you can just think log psi, or vice versa. So this primal form, the original elimination form, is very straightforward to write down for all of these problems. And each of the two well-studied ones have nice dual forms for variational inference. And so one obvious question, the way I've framed it, is what is the right variational form for these kind of mixed queries? It turns out you can answer that by first generalizing this set here into one unified framework. So instead of thinking about summation or maximization, let's replace the elimination operator with something we'll call a weighted sum. So it looks like a sum, but it has a little weight on top of it. And you can really just think of this as a power norm or an LP norm, where the power is 1 over the weight. Right, so if you know how to take an LP norm, that's all I'm talking about. The notation for writing LP norms doesn't work well for cascades of norms, so we had to invent this other one. And the reason this is a nice generalization is that this weighted norm can be thought of as being a temperature-controlled thing that can interpolate between sum and max or min. So for instance, if I take the weight equal to 1, then I just get standard summation, right? Sum of absolute values, but these are all positive numbers, so it's just a sum. If I take the weight going to 0 from the positive direction or the power going to infinity, I get max. This is a sort of low temperature limit. If I take it from the other direction, so I send it to minus infinity, then I get min. So all three of these operators are just different forms of this power sum for different choices of the weights. So now we can think about a more general, yes?
Was there any specific reason for choosing the notation this way, 1 over wi, instead of just wi to the power 1 over wi?
So writing it in terms of weights instead of powers?
Yeah.
Yes, it connects to the concept of tree reweighted. So these weights will correspond to the weights in tree reweighted. Yeah. So we could have called it power sum instead, but then we'd have had to invert to make that connection. Yeah. So now you can think about a generalization of the partition function, which is just a weighted partition function, where you've replaced all of the elimination operators by weighted versions, and you tell me what all those weights are. So this is just a more general problem that has weights associated with each variable. And each of these previous tasks just forms some special case of this problem. Right? So if I want to maximize over everything, I just take all the weights equal to 0. If I want to sum everything, I just take all the weights equal to 1. And if I want to do sum of each, then I take the set on which I'm summing and set them equal to 1, and the set I'm maxing and set them equal to 0. Right, so everything sort of fits this framework in a nice way. This weighted log partition function has a lot of the properties that have been exploited in variational methods about the log partition function. So it's convex. It has nice derivatives that correspond to marginal-like things. Its derivative with respect to weights can be shown to be an entropy, a kind of weighted entropy. So you need sort of the correct definitions for these things. But if you have intuition about the log partition function, it all carries over to this weighted form in a nice way. So now that we have this reframing of a more general problem, how can we approximate the weighted log partition function? So one easy thing is to just use Hölder's inequality. So this is some work I should have said a little while back. All of this from here on out is mainly the work of one of my students, Chang Lu. So this is one of his papers, was this Hölder's inequality application. So Hölder's inequality says if we have a weighted sum of a product of two functions, we can bound it by individually eliminating within them where we have weights associated with each of those things, and the sum of those weights is equal to the original weight. So the most common version of this is this main weight equals 1, and W1 plus W2 equal 1. So this is sort of standard PQ duality for summation. So now we can just apply this, where this is our partition function. Oh, I should say there's a nice reversal of this, the reversed Hölder's inequality as well. So I can lower bound this same sum by taking two weights, one of which is positive and the other of which is negative. So they still sum to W, but now they're of different signs. So this is not very well known. Everybody knows Hölder's inequality. This one has escaped the worldview, I guess. So this actually turns out to be a generalization of the mini-bucket algorithm I described earlier. So mini-bucket, we replaced the summation with a sum and a max. And if you just let your second weight go to plus 0, that's exactly what you get. Right? So this one will take the low temperature limit. If you replace it with 0 from the left, so power minus infinity, then you get a lower bound corresponding to sum and min. So if you use Hölder's inequality but take this infinite limit on your secondary weights, you'll get exactly the mini-bucket bounds. And so we can just replace those bounds within mini-bucket with Hölder's bounds. So think of the same procedure, same variable elimination procedure, but where I've now substituted sum and max by some arbitrary weights that sum up correctly. So they should sum to 1. And then do exactly the same thing, right? So this will give a different bound. And I'll show in a few minutes much better, actually. And also it has a nice symmetric lower bound from using the reverse Hölder's inequality. A useful way to think about this, so I drew this picture suggestively where we've split x1 and x2. This is actually a useful way to think about how to make choices. So we'll see one of the critical things is how should we choose weights and parameters within this. And the representation as a graph over split variables will give us a useful way to think of it. So if I take an original graph with cycles and I want to split it up into something we'll call a covering graph, there are many valid graphs that will be relaxations of this one. So I can choose, for instance, when I split x1, I can choose any weights that sum up to the original weight for x1. So any two weights that sum to 1, say. I also can choose my functions that are associated with either of those copies. So over here, we just sort of took the default thing. We had 3 functions. We put 2 of them over here and 1 over there. But we could multiply this by anything as long as we divided by it over here. So we're allowed some freedom of choice in what we allocate between those 2 copies as well.
Can you make the covering graph disconnected?
You can, but it won't help. So yeah, so it's not helpful to do that, and maybe I'll return to that in a minute. If that's okay. Any other questions? Okay, so so once we've got this framework where we have any choice of weights that are valid, any choice of parameters that are valid, we have a whole class of bounds, and we can ask how should we pick those weights and parameters such that we get the tightest such bound. It turns out that this formulation is very closely connected to variational algorithms. So in fact, if you set this up as just a minimization under some constraints, when you substitute Lagrange multipliers for those constraints and minimize over that new optimization problem, you find that it mimics exactly the variational form. So in fact, you can actually arrive, in fact, the variational form has been derived in a way like this without these bounds before. And you get, you can use these properties of the weighted log-partition function to get very similar looking results to what's known there. So you can, what you find is that the optimal points satisfy certain criteria, like the weighted marginal of one copy should be equal to the weighted marginal of another copy. And so you can take fixed point steps to try to enforce that. And it turns out that those fixed point steps will correspond to operations very much like and potentially equivalent, if you formulate them correctly, to the operations of message passing in variational algorithms. So you have a framework that lets you derive that algorithm, but it also gives you options to do other things as well, like directly minimize. It also gives you a nice framework for trying to optimize over the weights, because you can find that the optimal configuration of the weights satisfies an entropy matching quantity. So you can try to update your weights to enforce that as well. Interestingly, in the message passing form of this, this condition, the marginal matching condition, is very well known. That's what's being sought by the message passing operations. But the weights are actually not very much considered at all. So it'll turn out that this formulation is equivalent to these class of upper bounds like tree-weighted BP. And in tree-weighted BP, there is an algorithm for optimizing the weights, but it's to just use a conditional gradient update. So it's quite slow. And most people don't do it because it's also quite complicated. Whereas for us, it's extremely easy. We can either just calculate the derivative on the fly, or we can even take a moment matching kind of step. So it really sort of reformulates this in a nice and useful way. So coming back to this picture, where we had different algorithms and forms for each of these problems, this weighted mini bucket sort of fits all of these forms, as does the weighted log-partition function. And so you can just think of it all as being one problem, parameterized by whatever choice of weights you'd like to make. And this algorithm will remain the same for all of those choices. Okay? So over here, we'll now answer what this square should be. Oh, sorry. So before I answer that, let me return to this. So I mentioned that this weighted mini bucket form, right, running weighted mini bucket, is closely related to the tree-weighted variational algorithm. So if you choose your updates in a particular way and choose your weights in a particular way, you'll end up exactly with this tree-weighted algorithm. So why should you think about doing something in this primal form instead of running a message passing algorithm? It turns out that it's much, much more efficient to represent things using this kind of covering graph. So tree-weighted BP can be thought of as splitting the graph. So it takes the original graph and it splits it into a collection of spanning trees over that graph and gives each of them a weight. And then the message passing operators are defined by whatever the weights that you've assigned to those collection of trees is. And that's why people don't usually do this, right? You have to, if you do this directly, you enumerate a lot of trees and you optimize over their weights. There's a little bit more efficient way of doing it, but it only works if things are pairwise, so people really don't use it at all. In this formulation, it turns out that this single graph, this single covering graph for this grid, is equivalent to a weighting on any of these trees. So I have to describe for this bound, I have to describe a weight for each of these 4 copies. But if I were to do it in the tree-weighted formulation, I'd have to describe weights for every one of these trees. And here I also have to decide what allocation of parameters I have across those copies. Here I have to describe what allocation of parameters I have across every tree. So there's some explosion of the number of trees that one has to represent to get the same bound as any one covering graph. So this is much more efficient in some way. And all the parameters that have gone away are just locked at their optimal values. It's also really easy to use non-trees. So tree-weighted BP is sort of simplest to define for trees. And then there are versions for hypertrees as well. And conditional entropy decomposition is a generalization of those. But again, they're really not used in practice because it's very hard to try to enumerate over hypertrees. Right? You need to find some collection of hypertrees that you think are good. But the mini bucket elimination just goes through and produces these graphs in a very straightforward algorithmic kind of way. So it's controlled entirely by one single parameter, which is how large of a table you're willing to accommodate. So the code is really easy. There's only a scalar parameter to control. And it's easy to predict how much memory it will take. So you can choose that parameter so that you use as much memory as you have and no more. So here's just a quick example on comparing to tree-weighted and mini bucket for weighted mini bucket. So mini bucket by itself, this is just regular mini bucket, and this is tree-weighted on a small grid, so larger than that, but 10 by 10. So mini bucket also has this control over the table size, but it's not very effective. So it only starts to get pretty good once the table size gets really large. So here, this is width 8. So I'm able to accommodate tables of size 9, actually. So these things are using memory 2 to the 9th per function. And only at that point does it start to get better than tree-weighted. But if you just substitute the Hölder inequality, so this is actually the best thing tree-weighted can ever do. This is just, our weighted mini bucket is just selecting some graph and then optimizing over it. Suddenly things get tremendously better, such that they're a little worse than tree-weighted because we did this arbitrary graph selection for tree with 1, but for any size larger tables, you're already doing better. And one of the nice things about mini-bucket is that you can do it in a one-pass form. So in fact, mini-bucket has always been defined in one pass. And only with our algorithm do we sort of define iterations that could tighten it. But if you run our algorithm with just one pass, you do almost as well. So here was if you optimize for many iterations. Here's if you just do one step, so no iterations at all. And it degrades a little bit, but not too much. So this means that you don't have to worry about how many iterations things are going to take either. So message passing algorithms will tighten the bound, but they might take a long time to converge. And here, if you know, you can predict how much time things will take because you know what the table sizes are. And you can just allocate that time appropriately to choose whatever size you want. So in terms of timing and effectiveness, this gray curve is tree weighted. And just immediately, if you start to not do iterations but choose larger and larger tables, that turns out to be much more effective in terms of a time-quality trade-off. So this is a useful framework in that it lets you do that. Here's just another picture showing quality as you change this table size. So the quality really starts to get better if you can afford to have more memory associated with it. OK, so once we've defined this weighted log partition function, we can also take its dual, just as one would do for summation or maximization. And in that case, you get a very nice form. So in summation, it was an expectation plus an entropy. In maximization, that entropy had disappeared. And it turns out that in the mixed case, what you get is, well, so for marginal MAP in particular, where you have a bunch of maxes and then a bunch of sums, you get a conditional entropy. So your conditional entropy is on the sum terms given the max terms. And this, you can see, has the right endpoints. If I take the set B to be no nodes, so I don't maximize over anything, I get the entropy of the whole system. If I take the max nodes to be everything and don't sum over anything, I get the entropy of nothing. So it interpolates between these two endpoints. So it's somehow the right generalization of these two things. Moreover, you can use that to then define new message passing algorithms. So if you prefer to run message passing algorithms, you can run things like loopy-BP to solve this mixed marginal MAP problem. So in loopy-BP, we have the beta free energy approximation, or the tree-weighted approximation, or the mean field approximation. And here, instead of the entropy, we've got a conditional entropy, which you can think of as the full entropy minus the max parts entropy. So it's sort of truncating. Right? Take the whole entropy and then remove the part associated with the max terms. And so you can define versions of all of these things that are just truncated entropy versions. So you can find a generalization of the beta free energy to this truncated entropy, or tree-weighted, or any of those. And to see how that works out, here's just a really simple example. You can actually solve these kinds of marginal MAP problems by running loopy-BP. So loopy-BP will solve the expectation plus the full entropy. So let's say I run loopy-BP, I find a solution. But now, I didn't want to solve this entropy approximation. I wanted to solve the conditional entropy. So I'm supposed to subtract off the max part. So I'll do that by linearizing. So I just take my old model, and I take the part of the entropy that I'm over-including by including the whole entropy, and I remove it from the model component. So that just means I'll subtract log of my beliefs. And now I have a new model, and I can run some product on that again to try to optimize it again, and then again subtract the entropy as I go. So this is sort of iterative run of some product. Intuitively, you can think of this, it's kind of a proximal algorithm, but you can think of it like annealing. So what I do is I solve a summation problem, and then I look at all of my max nodes, and I add the log of their probability, log of their marginal. And so if the marginal probability is high, I'm going to make it a little higher. I'm going to encourage that kind of configuration. If the marginal probability is low, I'm going to make it a little lower. So it's just going to, everything's just going to get sharper as I go. So it's a little bit like annealing in that sense. Right? You run a summation problem, and then you push the max nodes toward whatever their optima should be. You can also define other algorithms. Sum product and max product like things, and they turn out a little bit differently as well. So this is a sort of double loop algorithm that use sum product in the middle. This is a sort of pure message passing algorithm. And it also turns out like, but somehow generalizing sum product and max product. So messages between sum nodes behave like sum product. Messages between max nodes behave like max product. And messages on the boundary have this kind of new form. So I won't explain this in much detail except to just say that you can generate many new kinds of algorithms like this. And often they have nice theoretical guarantees, although the reason I didn't talk about this in detail is that, at least experimentally so far, we've had more luck with this algorithm producing good solutions. This one has nicer theory, but has some convergence issues that we haven't sorted out yet. So again, here are some pictures. Here's that simple looking but classically hard problem. And here's performance as a function of how strong the interactions between the variables are. And this top thing is our truncated beta-free approximation. These are other things. Some of them are ours, like we have tree-weighted upper bounds. Some of them are other solutions, like simply running max product or running EM to solve it. Here's another picture for a more general graph. So in a simple graph like this, if I were to choose some configuration, I could actually compute the solution exactly given xb. Here's a loopy graph, so I can't even do that. So I have to approximate everything in the problem. And again, ours are doing much better than the others. Otherwise, I guess I wouldn't show you the pictures, right? Here on this problem, this is attractive models, so everyone wants to take on the same value. And we and several other algorithms are doing pretty well. But in mixed interactions, where some of the variables are changing the polarity of their preferences, in something like that, we tend to do much better. OK, so here's the picture again, right? 3 different forms of inference. This one much more general and less considered, but all of them unified in some combinatorial sense, right? If you write the primal version. And now we have versions for each of these problems in the dual, in the variational form. And all of those are actually also unifiable in a weighted sense. So it turns out that they all correspond to an expansion of the entropy with the weights attached to it. So in terms of the marginal MAP problem, you have a sequence of max nodes and then a sequence of sum nodes. And this expansion will give you that conditional entropy I showed earlier. So now both of these forms are unified in this nice way with only the choice of weights determining which problem you end up solving. So the useful thing about this is it lets us use these tools that have really become powerful either in the primal domain or in the dual domain to problems that have been very elusive. People really haven't considered them very much. So marginal MAP is one. Others that we're looking at are distributed decision problems, so coordinated decisions between actors in a domain. We're also interested in antagonistic systems where somebody's trying to minimize over something, let's say, as you're acting in the domain, and possibly games as well. So games have also been considered in variational forms. The framework also leads to a bunch of nice, very general algorithms that can be used on any of these problems. Even in just summation inference, which is really well studied, it gives you a new bound. It turns out that these are equivalent to another known class of bounds, but they're much easier and more efficient to implement and much easier to optimize. It lets you do this on mixed inference problems. So I already mentioned this MAP. I really think that things like marginal MAP are problems that we ought to be solving. So I think people don't solve them because they don't know how. So they just replace them with this solver that they know they can get to work. And so now that we have tools that work on it, I'm hopeful that we can start seeing things change so that we use the appropriate inference problem to whatever problem we actually want to solve. OK, so thanks. Oh, and I should mention this is partly funded by NSF. And my student, Chang Lu, who worked on it, is also funded by a Microsoft fellowship. Thanks.
Any questions?
So previously, like when people were doing the simpler like sum and max problems before there was like the weighted mini bucket generalization, and they need to choose how to split the graph and how to put the weights for like the size and stuff like that. Were they essentially doing like the same optimization that you're doing, but just with fixed W's, or was it more arbitrary?
Right. So for summation is where the weights become important. In max, they're all 0, so it doesn't matter so much. There are so the original paper on tree weighted used pairwise graphs. And in pairwise graphs, you can optimize over the weights for your trees using a gradient step. But as soon as things are not pairwise, or you try to use clique sizes that are greater than 2, that breaks down. And so maybe I'm just unaware of them, but all the implementations that I have seen by other labs all do a collection of randomly chosen trees, don't optimize over the weights at all. They just pick them at random or set them to 1 over n or something like that.
So this generalization would
so in this case, it's really
more
easy to optimize over the weights. And in fact, you can optimize over the weights just on the downward pass. And actually, that works better than randomly chosen ones. Yeah. Yes?
So in the bounds you're computing, I think there'll be certain graphs where the bound is tighter than the other graphs.
Sure.
So what are the characteristics of graphs where the bound may not be tight?
Yeah, so it's difficult to characterize, but if so I showed a couple of pictures that will at least suggest how to answer that. So, yeah, so this is not as helpful. Let me find a graph that's not the right graph, but we'll show it. So if one of the standard examples for this in a theoretical paper is to just run it on an Ising grid, so binary variables in a grid. If those variables are attractively coupled, so they all want to take on the same value, you tend to see an arc like this. So you do very well when things are weakly interacting. It's approximate still, but you're quite good. There's some regime in which you're doing as bad as possible. And then once everything becomes locked in so that it wants to do all of one state or all of another state, you start doing really well again. If you're in either of those two regimes and things are attractive, you'll do well. If things are mixed, so you have some kind of frustration in the cycles, then you usually don't see this decline anymore. So then you see things getting worse overall. So then you'll do best mostly in this weakly connected regime.
In general, is it also safe to assume that the more loopy the graph is, the worse the bond would be?
Typically, yes. Although it's an interaction between loopiness and strength in some sense.
But for trees, you always have a good bound, right? Tight bound.
Trees, it always, well, so marginal MAP, no. But for trees with summation or maximization, it's trivial to compute exactly. Yeah, you just order it using dynamic programming.
Yes, Ron?
So the entire talk really assumes that things can be nicely factored into a factor graph with, functions of a small number of coefficients.
Yeah.
Now, can you comment when that approximation starts breaking down, how do you treat the problem?
So any problem to be tractable in some sense, you need to at least be able to evaluate the probability distribution. So if things are totally arbitrary on a distribution of n variables, I don't know how to represent that. But if you have some compact form, then it might be possible to use methods like this anyway. So in fact, everything I've been talking about sort of assumes these tables are completely arbitrary. But there's a line of work in message passing and approximate inference that looks at structured functions. So if your functions, even if their tabular representation would be very large, if they're easy to solve themselves, so things like matching problems that you can solve using auction algorithms, for example, those can be used by virtue of them being compactly representable and solvable. So if you don't have that, then I don't quite know where to go. But
Can I ask one quick question?
Yeah, please.
It's not exactly related to the optimization method that you showed, but I'm just curious that in the context of graphical models, do you guys ever run into problems of inverse inference, which means that, say for example, the exact topology of the graph is not quite known, like which random variable is connected to which random variable, for example. Maybe the inference is given to you, and from the inference, you're trying to kind of like, back identify what the topology of the graph is. Now, in such problems, do you run into issues of non-uniqueness, which means that first of all, the topology itself may be different for the same kind of inference, or for the same topology, there may be a different distribution of weights for different types of graphs which produce the same inference.
yeah, so the most common framework that matches, I think, what you're saying is the standard learning problem. So if I have some data, I can take those data and I can compute moments in the data or some features that I want to represent in my model, and then I want to learn a model that reproduces that behavior. So there's both structure learning, where I don't know the structure of the graph, and I'd like to know what variables depend on what. And even given the structure, just parameter learning, what parameters of the model will reproduce those moments.
Let's say, for example, if there's a question of non-uniqueness, like for example, there may be 5.
Yes, so right. So among, in fact, given a set of moments, there are many graphical models that will produce those. For instance, if I give you any graph and I make it more complicated by just adding another function, it's perfectly capable of representing the same distribution. So usually what one means when you do, say, structure learning is you want the simplest possible explanation.
So there's some constraints with respect.
That's right. Yeah, and under that, it probably is still non-unique, but at least it's well posed, right? So you have a minimization problem. There might be two graphs with equal numbers of parameters that represent the data equally well, but at least you've now got a single minimization problem, so you're finding some optima of it.
But when you pose the constraint of finding the simplest, in some sense the simplest graph or something, the graph which you will finally end up identifying, that may not exactly be the true graph, right?
Yes, it absolutely might not be the true graph. Yeah.
All right. Well, let's
Thanks. Thank you.